Okay, so let's talk about clutches and brakes. Purpose Previously, of course, we'd been talking about stuff where we're trying to minimize friction. Gears, bearings, so on and so forth. Now it's the exact opposite. We're trying to maximize our friction. So we're trying to use the clutch or the brake to friction's the mechanism via which these clutches and brakes work. So we're using friction. We want it maximized. We want we want it maximized to a degree. Obviously, we're not necessarily going to do things that maximize that friction. Well, if other effects will be, uh, if that'll cause other effects, when we could get instead a reasonable amount of friction and say reduce the wear. We'll talk about that in a bit. But we generally want to ensure that we're having a uniform coefficient of friction so that our braking power stays constant. Uh, we want to be minimizing wear. Again, we previously we generally tried to do so by say avoiding contact, so avoiding metal on metal contact with our hydrodynamic bearings. Can't do that. So just need to we still need to minimize the amount of wear that occurs, and that's typically going to be a matter of to a large degree material selection, as well as ensuring the heat doesn't build up too much, because that'll cause your wear to jump up. So for clutches, you want to have gradual connection and disconnect of two members that have the same axis of rotation. So, you got a shaft that's rotating, coming from say an engine, and you want to connect that to the wheels so you can start rolling. Then we can use a clutch to do that. Brake, it's basically exactly like a clutch, but instead of two members that are rotating, one of them's not rotating at all. So we're trying to take a member that's already rotating and slow it down and or stop it. So the force needs to be produced by an acceptable attenuating actuating force. So we need to be able to uh, engage the clutch or engage the brake by applying some sort of reasonable force. Heat's going to be generated when we're using friction, obviously, so we need to be able to dissipate that without having our temperatures rise too much. So again, like I mentioned, when stuff gets too hot, and then we're gonna see too much wear going on. So where characteristics need to have an acceptable lifespan, that plays into the other stuff as well. If we need to have too high of a force to generate the torque that we would want, and if as a result the heat would spike too much, then our wear characteristic would be then our wear would be unacceptable. So here's just kind of uh, a simple clutch. We've got a driving shaft right here, so this is rotating, and then we got a driven shaft here, so it might not be rotating when we start, or it might be rotating at say a different speed, but essentially some we have the contact face here on the driven shaft come into contact with the friction lining material here, and then once they come into contact, essentially that'll cause that friction between the two surfaces that are moving relative to one another is going to transfer torque from the driving shaft to the driven shaft. So the contact surface that we're looking at here could be looked at. We could see like a little ring element here. So kind of like an infant. Our dr is going to be the thickness of that ring element there, and then obviously the length, the area of that ring element is just a function of the radius that we're looking at. Bit more complicated. So this is an example of one you might see like an automotive. So this lever here can be used to engage or disengage the clutch. So this will kind of when we move this lever, it presses this housing down here, which causes the this pressure plate up here to press against the clutch plates, to press against the clutch plates and the friction plates. So those engage with the uh, sorry. Okay, so we got the friction plates, two friction plates here. One friction plate's kind of attached to the flywheel. The other is attached to the pressure plate, and then in between the two, they got a we've got a disc here that's kind of attached to the output shaft, so it kind of gets pressed between the two. Here we got a different version, so this is a hydraulically actuated one. So oil pressure will be put in sorry, we'll pump oil into here, which causes pressure, which pushes this together. So then we've got these discs here that are attached to this housing here. So this housing here is attached to the output shaft. The input shaft's on this side, and that's attached to the these driving discs. So these discs here that are attached to the input shaft. So when the clutch gets engaged, the driving discs are pressed together against the driven discs, and we're able to, and then torque gets generated and stuff starts turning. So oftentimes in a lot of actual clutches, you'll have setups like this where you'll have friction discs that are pressed between two surfaces when it's engaged, in order to kind of even out the in order to basically eliminate any bending moment on that disc or what have you, and to double the amount of surface area that you're using to generate that torque, which it essentially increases the amount of torque that you can transmit as a function for a given size of clutch. So there's two kind of assumptions we could use to kind of do our torque calculations. There's the uniform pressure assumption. So if we're pressing kind of the disc together, and if we're assuming that there's a uniform if we assume that the pressure is distributed equally across the disc, then again we can kind of examine this ring element that we talked about, and it's going to have a certain amount of force applied to it. So again, pressure times just the area of that ring element, circumference times the thickness of the ring, basically here. And then of course the torque generated by that force distributed over that ring is just going to be that force times the radius. And the and then of course this is the pressure kind of pressing down. This is normal force. So if we want to translate that normal force into the tangential force, basically, which is going to be transmitting our torque, that's a function of the coefficient of friction. So we take this normal force, kind of distributed over that ring, multiply it by the coefficient of friction to get our tangential force, and multiply it by the radius to get our torque. So that's the torque over that tiny little infinitesimal sized ring. Obviously, we get the total torque just by integrating. So that'll give us this, if we are assuming that the pressure is evenly distributed. Problem with that is that once you get these things in operation, they're going to wear away a little bit. And in general, oh yeah, sorry, I skipped ahead a bit here. So that calculation would be based upon a per mating surface. So again, like I said, actual clutches will typically be using an even number of mating surfaces. So we got friction discs that are pressed between plates on either side. So that's what this N is for. So we can, and if we want to relate this in terms of not the pressure, but in terms of the kind of like the pressure over the surface, but in terms of just the total force that's being applied, we just need to kind of sub in that pressure value for, we know that P is equal to F over A, so just sub in F over A here. So this formula here gives us this formula here on the bottom is what gives us the torque that can be generated as a function of the clamping force, the number of mating surfaces, the coefficient of friction, and then the inside and outside diameters. Oh, sorry, inside and outside radiuses. Diameters, I mean, I'm sure you can divide by 2 if you need to. So, again, this is for the uniform pressure assumption. Problem is that, okay, so when things wear away, they're going to wear away at a particular rate. In general, wear happens at a rate that is proportional to how fast something is sliding relative to the surface it's sliding against and the friction force. So if we assume uniform pressure, then what's going to happen is that the outside surface of the clutch is going to have a higher wear than the inside surface because the sliding velocity is higher, because it's further out. Spinning. If they're spinning at a uniform rotational speed, the portion that's further away from the center is going faster, meters per second or what have you. So as a result, essentially what's going to happen is if you start with a uniform pressure distribution, then what's going to happen is you're going to get more wear happening on the outside than on the inside. And that's going to change your pressure distribution, because essentially if you start out with, essentially kind of like a nice really flat surface, and you press those two things together and more wear happens on the outside, then basically, essentially, you disengage a little bit. If you kind of measure like the gaps the gap on the outside is going to be a bit larger than the gap on the inside. So when you go and re-engage those, they're not going to come together the same way. What's going to happen is that they're going to because the outside surface was worn away a bit more than the inside surface, the pressure that you can get when you clamp those two parts together is going to be less on the outside. So the uniform wear assumption it takes into account that the wear changes the dimensions of the mating face as a result of that. So what we say is that basically, and again, keeping in mind that the if wear is proportional to the sliding velocity and the friction force, then basically if we assume that wear is constant, like kind of the wear rate is going to be constant over the entire face of the surfaces that are clamping together, uh, then then that leads to a uniform rate of friction work. So if our dF over V is going to be a constant, then basically, and we know that R is that the velocity, the relative velocity is proportional to the radius, then we can say that our PR is going to be constant. So the if the PR is going to be constant, then that means that you get a decrease in the pressure that you see, a decrease in the actual pressure that would be experienced after a bit of wear has occurred as you move away from the outside. There's going to be more pressure on the inside, less pressure on the outside, but a relatively is going to be a higher velocity on the inside and a lower relative velocity on the outside. So that comes into play there. So essentially, this C is going to be based upon kind of like the highest pressure that the mating surfaces can withstand without wearing away, and the inner velocity. So the pressure is going to be highest. So kind of once we get into a bit of a steady state where kind of that wear pattern has been established, the constant is going to be based upon what sort of pressure can be withstood by the mating materials. So again, similar way, we got our F. We know that that'll be kind of, we can figure out what's the F in terms of that pressure. The torque can be found in terms of sorry, the torque can be found in terms of that pressure, and then essentially once we go to kind of plug substitute this equation into this one, then we're able to find our torque total in terms of the total of clamping force that we're using, the coefficient of friction, the number of plates we're using, the number of mating surfaces we're using, and then just the outside and inside diameters. So typically speaking, this uniform wear assumption is more valid for anything but a brand new anything but a brand new clutch. What happens is that when you get a brand new clutch, it's going to have a bit of a working period where it has a higher torque that it can transmit than it then you're going to see later on down the road. So typical values depends upon what we're using for the friction material. And again, each of these is kind of when we're rubbing it against smooth cast iron or steel. So we're assuming that we're sticking at least one of the mating surfaces is going to be steel or cast iron. And we're going to get a dynamic coefficient of friction based upon what we're pressing it against, and this is for the operating dry conditions, so that's without any oil. And then this maximum pressure here Again, that's kind of what's used to calculate this C value here. But that maximum pressure is going to be dependent upon the material as well. And then again, we're also going to get maximum temperatures that particular material is able to withstand. And again, you can get fairly high ranges. Like sintered metal will depend upon what sintered metal you're talking about, obviously. Yeah, it's those are kind of the value. Those are where you can look up a reasonable value for your dynamic coefficient of friction. That's in the operating dry condition. If we are looking for operating in oil, which you may be doing in order to decrease the amount of wear that occurs, and also help help your heat transfer, help dissipate heat away from the space, then you may be operating in oil. So in that case, you're going to get a lower dynamic coefficient of friction, but so be it. And if once you know your dynamic coefficient of friction, then essentially, and of course how much clamping force you can provide, then and again, I'd like to keep in mind that the clamping force you can use is kind of based upon here. Based upon the material, we're limited by maximum pressure, but once we know our clamping force and our coefficient of friction, and of course obviously our number of plates, then the torque value is going to be based upon the ratio. The torque value is going to be based upon what we get here. So that our RO plus RI. So typical values are going to be between 0.4. For a given maximum outer radius, because obviously we're limited on the maximum overall size, but for a given maximum size for the outside, the inner side, we could change the radius. We could change basically the size of kind of the ring that we're using. So we could have an inner radius that is a certain portion of the outer radius. So typical values are between 0.45 and 0.8 RO. Turns out that the optimum value basically ends up being at 0.84 RO if we want to maximize that. If we want to maximize the amount of torque that we're going to be generating for the uniform wear assumption. Again, that's for a given outside diameter. Brakes. Instead of clutches, like I said, they're fairly similar. Problem is that cooling tends to be more critical for brakes. So as a result, we don't tend to get this like disc pressing against a disc thing, because we need the exposed surface area of the disc as it's of the brake as it's rotating around to help dissipate heat. So there needs to be a portion of the a portion of the brake that allows you to that allows convection to occur to help you dissipate your heat. So the surface of the brake disc needs to be cooled by convection. We often get these air cooling passages built in as well, and the housing here might have some cooling fins added as well. Other than that, so our torque available for braking calculated in the same manner as the clutch, but again, we're just not integrating over the entire disc face, just the portion that comes into contact with the pads. So basically, if we go up to here, then we're just going to be, essentially we're not using kind of the assumption that the area that comes into contact is the full size ring. It's only a portion of the ring, and this, the portion of that ring can change as you go from the inner side to the outside. So that'll depend upon your brake geometry. One other form that can be useful is conical brakes and clutches. So we just talked about kind of the way that V-belts work. They basically increase the effective coefficient of friction, allowing them to transport more torque by wedging themselves in. Well, guess what? Conical brakes, conical clutches work the exact same way. Same mechanism. So we got this cone angle here, alpha. Again, they used alpha. I would kind of wish that they'd used beta, because again they used beta for the V belts, and that would have been nice. But they used alpha, so be it. I'm going with the nomenclature in your textbook. We just basically take take the same formula that we used for the uniform pressure assumption and divide by sine of alpha, or take the same formula that we'd used for the uniform wear assumption, divide by the sine of alpha. So that allows us to substantially increase the kind of our torque generating capacity. With the downside is that with a cone like this, we can't really use multiple surfaces. But that having been said, like if we have an alpha of say 10, if we have an alpha of 10 degrees, then that is the equivalent of using 5.75 discs. So we're able to kind of fit that in using smaller surface area and using kind of fit that into a smaller space, use up less mass by taking advantage of that wedging action. So generally speaking, you don't use less than 8 because 8 degrees for your cone angle, because that has more of a tendency to kind of once it engages it, if it's too small of an angle, that has more tendency to kind of get stuck. So you're less likely to be able to disengage when you want to. So that would be a bad thing. So typically speaking, 8 to 15 degrees is what's often used for that. So yeah, let's look at an example. If we have a multiple disc wet clutch, so here, and again, this is not the one that we're looking at. This is just an example of one of those. So we're trying to find the total number of discs. So this one uses 3 driven discs for 6 friction surfaces. We're trying to find how much we want. So we want the outside diameter of the disc to be 100 millimeters. So our RO is going to be 50 millimeters. Our coefficient of friction is going to be 0.06. And the Pmax is going to be 1400 kPa. And we're trying to transmit at least 85 Newton meters of torque. So we want to find out an appropriate value for Ri and our number of mating surfaces and an appropriate clamping force. So let's just go ahead and make an assumption here. Let's pick an Ri that's equal to 0.58 RO. So that'll be 29 millimeters. So if we're going for 29 millimeters, so we got our Ri, we've got our RO. We can go ahead and figure out what our clamping force is going to be based upon our Pmax. So I'm just gonna grab that here. So we know that our Pmax is well, 1.4 megapascals. So our clamping force is going to be equal to 2 pi times 1.4 MPa times 29 millimeters times 50 millimeters minus 29 millimeters. So let's see here. 2 times 3.14159 times 1.4 times 29 times 50 minus 29 brackets, blah, blah, blah. So again, units, the way our units cancel out, we've got millimeters squared here, we got MPa here, so an MPa is a Newton per millimeter squared, so we're just going to get straight newtons shooting out the end here. So that'll be 5.36 kilonewtons is going to be our clamping force. So based upon that, again, we can just go up to this formula here. So we know what torque we're trying to target. I'm going to try to target 85, not 58 Newton meters, and that needs to be equal to FF RO plus RI over 2 N. So if we just want to solve for N, then our N is going to be 85. I'm going to say 85,000 Newton millimeters, all divided by R F. So times our coefficient of friction. What was that? That was 0.06. Times our RO plus RI divided by 2. So 59 plus 50 divided by 2. That's an ugly looking 2. That's in millimeters. So again, millimeters cancel out, newtons cancel out. And we're left with a number, an integer value. And that is so that gives us 6.7. So we'd need at least 6. So again, typically speaking, we want to keep an even number there. So we're actually going to go with an n of equal to 8. So that'll be 8 mating surfaces. So like we'll have 4 of our discs. And that'll kind of be attached to the one side. And then on the other side, it'll look something like this. So something like this. And then, pressure is going to be applied to this side, and like this one, these ones are going to kind of be held in place, and then that'll basically, and then obviously all of these can move a little bit, so that when that pressure gets applied, the clamping force gets adjusted, and then when the pressure is released, they kind of separate enough that there's no clamping force, and thus no torque transferred. But yeah, that would be that.